We will start now our session number 5, the last session in the conference, entitled number 2. I hope that we are not going to speak at the end of the day. One of the chairpersons are my colleague, Professor Hubrich, together with myself. Our first presentation is from Professor Martin Hubrich, online. Professor Hubrich is Institute, Germany, with the chess interests are with main subjects of chemical and mechanical process engineering. Hello, good morning, Professor. Do you hear me?
Yes, I can see and can hear you proper. I hope you can see my presentation.
Great. You see yes. Go ahead, please.
Thank you very much for the introduction, and I would like to thank you to get the chance to present here the second time. And it's a pleasure for me to join all these interesting presentations we heard today and yesterday. And I would like to give you some ideas about iron and steel production and the water treatment and recovery, which has changed in the last years, and some applications we are working on. We are BFI, we are a non-profit center, and we are dealing with all subjects regarding iron and steel industry. So what we are dealing with is with water scarcity. So a few years ago, nobody was thinking about water stress in Europe, and but the point of view has changed. And now it comes a need to find out suitable technologies to recover water, to save water, and to open up new water resources to ensure the production processes and to produce a suitable amount of water which has a sufficient quality and a sufficient amount. So the further conditions at the situation are that we have a change of the iron and steel production industry with new wastewaters coming up. And for the change from carbon to H2-based steel production, we have an additional water amount, which is only for Germany about 2.4 million cubic meter of fresh water. And further on, we are getting more and more strict rules regarding water and closing circuits. So the idea of EU is to have only zero waste at the production sites, which should be related and realized until 2050. So that means we need new technologies, we need new water resources, and we need to decouple production from freshwater demand. So I'll give you an idea about the amounts. In steel industry, EU 27, we have a demand of 2 billion cubic meter of fresh water per year, and about 75% is used in cooling applications, and the rest in material conditioning and gas washing, for example. So our idea is to use the technology of membrane-based capacitive deionization, which is based on electrostatic adsorption. That means you have two different periods. You have one period while you are having a current at the treatment unit where you are collecting the ions and produce a desalted water. And you have a second period for regeneration of the module while you are changing the current, and you will release the ions and you have a concentrate flow. So the advantage of this is that you can adjust the water quality by just changing the energy intake, and you produce the water quality you would like to have. On the right-hand side down, you can see an exemplary diagram for current, voltage, and flow rate. So further on, you can see on this slide two applications, one a lab unit and one pilot unit with a capacity of 2 cubic meter per hour. What we saw in our investigations, which were performed mainly at first with cooling waters, that we saw in some cases that we have lower energy demands than compared to reverse osmosis. So on the next slide, I will present you results from 3 different sites. First site was a treatment of a backwashing water of a sand filter of a hot rolling mill. We have the aim to produce water with conductivity less than 200 microsiemens and chloride less than 50 milligram per liter. And on the right-hand side, you can see the water which is coming in. That was the black one. And of course, we cannot dissolve this water with any technology before a suitable treatment. And the pre-treatment, which was determined as suitable, was a combined dissolved air flotation with microfiltration to fulfill the requirements. And what we did there is the investigation of the MCDI and the reverse osmosis over several months to have a reverse osmosis as benchmark and to see what is the best technology for this application. So we performed several optimization. And what I would like to show you here on the next slide is that you have here a figure about a period of 3 weeks of operation. And the red continuous line is the feed chloride content. And you can see that is varying very strong between 60 to more than 160 milligram per liter. And what I would like to point out is the red dotted line with the chloride content of the produced pure water of the MCDI, which is about 30 milligram per liter. The same is for fluoride and for sulfate and calcium, that we have more or less constant values. And this is very important for all the following production process, that you can be sure that the water quality is always the same and has no impact coming from production or for seasonal impacts as well. So we achieved the operational requirements, and we had a water recovery about 78% with an energy consumption which was lower. I will just show you on the next slide. So after 3 months of field trials of both plants, reverse osmosis and MCDI, we can consider that the MCDI had a 22% lower energy demand than the reverse osmosis. And the water recovery rates were in the same range. So for MCDI, it's about 80%. For reverse osmosis, it was about 85 to 90%. And the conductivity, of course, is different, but it's always the question, do I need the high quality water from reverse osmosis, or is it just sufficient to decrease the iron content and the conductivity to a certain amount with a lower energy demand? So then we were taking a look, what can we do with this water? And we can use this water as it comes from the MCDI in 11 from 12 possible application in iron and steel industry. And we adjust in some cases to adjust the pH value about 0.5. So the next application is the direct cooling water treatment. We have a similar aims than before. And what we found out in lab trials, that it was possible to fulfill the operational requirements with water recovery rates about 74%, and reduce the chloride and sulfate content below 50 milligram per liter. So it seems everything was fine. And then 6 months later, after the lab trials, we started the field trials. So during the field trials, we had a surprise that we noticed that the desalination capacity decreased from 75 to 30%. And then we take a sample from the site, investigate it at the lab, and we had the same effect as described here. So we started an investigation, what has changed in the time in the last 6 months, and investigated the documentation of the cooling water. And then we found out that there have been a change of the used coagulant, and that the new coagulant has a factor 2 higher active agent content. And further on, the water intake has been reduced, while the organic content has been more or less doubled. So all these impacts together led to this change of the desalting capacity. So what we tried is to find out how can we dissolve this problem. And we did it with activated carbon, but this did not have any impact. So we started an investigation of the different products which were used at the site. So what you can see here on the top is the green dotted line. This is the removal efficiency with no chemical dosage, and it's constant. And on the bottom line, you can see a green line without any chemical dosage, and you have a pure water conductivity, which is below 200 microsiemens per centimeter. But in the case, if we dose the coagulant and the flocculant, which were both used in this cooling water circuit, you can see a significant decrease of the removal efficiency, and in parallel, the conductivity of the pure water is increasing as well. So what we find out is that there are some components in a certain amount or some products which can affect the efficiency of the MCDI. And now currently we are working on in a new running project to find out what is the single component which will interact with the ion exchange membranes. So after studying literature, there are several hints that say that some components can affect interact with the ion exchange membranes. But to point this out, we are performing right now a research project, and I can present these results next year. So what we did further is we investigated the water from a central treatment plant, and this is a new approach we have been looking for, to look for more complex waters to go to wastewaters. We have about 15 different inlets, and we have different wastewaters which were mixed together from a gas washing, from hot and cold rolling, surface treatment. So you can see it's very complex. And we have two different operational conditions. One is without dosing from the biological treatment plant, and the other with. And we have a variation of the parameter about 3 to 5. So finally, after the optimization, you can see the results here. We were able to fulfill the operational requirements for an internal reuse of the water. And without discharge from the biological treatment, we have a water recovery about 56%. And with it, we have about 70.
Please, 1 minute.
And so to summarize it, the MCDI is suitable technology for the treatment of cooling water. There are some rare applications where we have disturbing influences where we are looking for. And we see MCDI as a possible technology for treatment of wastewaters as well. But of course, at a certain point, RO is a more applicable technology depending on salt and the TDS content. But below, we see MCDI as a technology, and we are looking for new applications, and we are currently working on it. Thank you very much for your attention, and I'm open for your question.
Thank you very much, Professor Hubrich. And any questions? You have questions from the audience?
We have time for 40 questions.
Well, thank you. Go ahead, please.
Very nice talk. You have serious cooling problems with steel plants using membrane technology.
I'm sorry, it was very I did not hear the question.
Membrane fouling problems in steel plants using.
We have by the time you have to clean the MCDI modules, you can do it on an automatic way, just with having using compressed air, or you have the other application yet that you can use acid if it is possible. It depends on your application. So and the hardness contents. Regarding biofouling, we did not see any effect in all the applications we have been investigating.
Right. How about increasing the theta potential of the effluent? If you charge the theta potential, increasing the theta potential, can you, avoid the following problems to some extent? Theta potential of the, of the effluent.
I did not get the question right now. It was a
increase the charge on the fouling on the effluent. Increase the theta potential of the effluent. Can you avoid the fouling problems?
Yes, you can just clean at a certain point. We were investigating two different kinds of MCDIs. We have a standard one, which is now available on the market. And now we are having a second one, which has modified ion exchange membranes. And what we saw there, that is not that sensitive compared to organic loads or the flocculants or coagulants. We did not see any impact when we are working with the modified membranes. It's working perfect. And to avoid this fouling, we have the chance to dose an antiscalant, for instance, when we are using the regeneration. So during the operational process, when you are removing the ions, you are not getting in that area that you have an oversaturated solution. But when you are regenerating your modules, then you release ions, you have a comparable low water flow, and then you are in the danger to having precipitation residues. And this you can avoid in two ways. One is to add during that time an antiscalant, or the other one is to have a higher regeneration flow, or just regenerate more often. But this leads to a decrease of the efficiency and the flow rate you can treat.
Okay, thank you very much, Professor. We highly appreciate your presentation. Thank you very much.
Thank you very much.
Welcome, sir. Now.